The ship does not ease into the water. It crashes into it. On a gray morning in Newport News, Virginia, a structure the length of 3 city blocks and the height of a 20-story building begins to move. Slowly at first, almost imperceptibly, as if the earth itself is reluctant to release it. Then faster. The hull accelerates down the greased slipway and strikes the James River with a concussive boom that shakes the chest of every engineer watching from the bank. A wall of displaced water rises and falls. The noise fades. And then something happens that should not be possible by any ordinary measure of common sense. That mountain of steel, roughly 104,000 tons of it, quietly, almost lazily, settles onto the surface of the water and stays there. Not for a moment. Indefinitely. The question is not why it floats. Everyone learned Archimedes in school. The question is what it actually means to apply that principle at this particular scale, because the honest answer is stranger and more elegant than the textbook version ever suggested. A Nimitz-class aircraft carrier is the largest warship ever put into sustained service by any navy in human history. It is powered by 2 nuclear reactors. It carries roughly 6,000 personnel, 80 aircraft, and enough aviation fuel to sustain combat operations for weeks without resupply. Its flight deck is roughly 333 meters long and 77 meters wide, a paved surface the area of more than 4 American football fields suspended above the ocean. The ship beneath that deck is not a solid block of metal. It is a precision-engineered argument against its own weight. And by the end of this, you will understand exactly how that argument works, and why the engineers who built it made choices that seem, at first glance, completely backwards. Start with the physics, because the physics here is unforgiving. Archimedes' principle states that any object placed in a fluid is buoyed upward by a force equal to the weight of the fluid it displaces. The fluid is seawater, which weighs roughly 1,025 kilograms per cubic meter. The object is a carrier. The math is not optional. If you want 104,000 metric tons of steel, aircraft, fuel, crew, weapons, and reactor shielding to float, you need to displace a volume of seawater that weighs at least that much. Work backwards through the numbers. 104,000 metric tons is 104 million kilograms. Divide by 1,025 kilograms per cubic meter and you arrive at roughly 101,500 cubic meters of water that must be pushed aside. That is the minimum. In practice, a Nimitz-class hull displaces significantly more than that, somewhere in the range of 280,000 cubic meters of enclosed volume in the hull structure, because you need margin, stability, and reserve buoyancy beyond the bare displacement figure. Now here is where common sense breaks down. Most people, if asked why a steel ship floats, will say something like, well, it is hollow. And that is true but deeply incomplete, because hollow in what shape matters enormously. A flat steel sheet that is technically hollow can still sink if the geometry is wrong. A steel ball can be hollow and still float if its enclosed volume is large enough. The trick is not just emptiness. The trick is the ratio of total enclosed volume to total mass, and the geometry of that volume, specifically where the center of that enclosed mass sits relative to the waterline and relative to the ship's center of gravity. Think of it this way. Imagine you are trying to carry a very heavy person across a swimming pool on a foam kickboard. The kickboard alone will not work. But if you attach enough kickboards underneath, eventually the combined buoyant force of the foam, each piece displacing water weighing more than itself, lifts both you and the person you are carrying. The steel hull of a carrier works the same way. The steel itself is dense, roughly 7,800 kilograms per cubic meter, nearly 8 times denser than seawater. Left to its own devices, a solid block of that steel would sink immediately. But the hull is not a solid block. It is a shaped container. The interior of that container is filled largely with air, with machinery spaces, with compartments, with corridors and crew quarters and fuel tanks and aircraft hangars. That air contributes almost nothing to the weight. It contributes enormously to the volume. The average density of the whole assembled ship, steel skin plus all that air-filled interior, works out to be less than the density of seawater. That is the entire trick. A carrier floats for the same reason a bathtub floats if you set it right side up in a swimming pool and do not let any water over the edge. Which brings us to the part of the engineering that nobody talks about in the textbooks. Floating is the easy problem. Staying afloat when things go wrong, that is the engineering that matters. The hull of a Nimitz-class carrier is not a single open chamber. It is divided into roughly 2,000 watertight compartments. This is not an accident of construction. It is the central structural logic of the entire vessel. The lower portion of the hull, below the waterline, is divided by transverse bulkheads running across the width of the ship, and longitudinal bulkheads running the length of it, creating a grid of sealed cells. If one compartment floods, the water stays in that compartment. The surrounding cells remain dry. The loss of buoyancy is local and calculable, not catastrophic and total. Here is a real number to hold on to. If a carrier takes damage below the waterline and a single compartment floods, the ship might settle by a few centimeters and develop a slight list, a tilt to one side. Engineers counter this with ballasting, pumping water into tanks on the opposite side of the ship to rebalance the weight distribution. The carrier continues operating. This is not a hypothetical scenario. During exercises and operational service, naval engineers run damage control drills that deliberately simulate compartment flooding to test exactly these responses. The USS Forrestal, a carrier that suffered a catastrophic fire in 1967, offers an instructive case. That fire killed 134 sailors and caused devastating destruction to the flight deck and upper hangar. But the ship did not sink. Despite extreme structural damage, fires burning through multiple decks, and the detonation of weapons and fuel on board, the compartmentalized hull below maintained enough intact buoyancy to keep the vessel afloat. The Forrestal eventually returned to port under her own power. The compartment grid held. Which brings up the false belief worth correcting directly, because it is almost universally held. Everyone assumes that the danger to a large ship is that it will simply tip over sideways, that it is a stability problem, a question of balance. Designers certainly think about stability. The carrier's hull is designed so that its center of buoyancy, the geometric center of its underwater volume, sits directly below its center of gravity when the ship is level. When the ship rolls, the center of buoyancy shifts outward in the direction of the roll, generating a restoring moment, a force that pushes the ship back upright. That is real and important. But the engineers who lose sleep over a carrier's survivability are not primarily worried about tipping. They are worried about progressive flooding. A ship that tips can often right itself. A ship that progressively floods, compartment after compartment as water finds paths through damaged bulkheads, loses reserve buoyancy incrementally until the displaced volume can no longer support the weight above it. The engineering response is not to make the hull stiffer or heavier. The response is to make the flooding local, permanent, and bounded. Seal off the damage. Preserve the intact cells. Maintain the ratio of enclosed volume to total mass above the critical threshold. The carrier does not fight flooding by being stronger than water. It fights flooding by being smarter than water. Consider the scale of what that means in practice. A Nimitz-class carrier's hull plating at the keel, the very bottom of the ship, is roughly 65 mm thick in the most heavily stressed sections. The ship's total weight presses down at roughly 104,000 tons. The water presses back up at exactly the same force, distributed across a whole bottom area of thousands of square meters. The engineering is not dramatic. It is precise. The pressures involved are well within the material capacity of the steel. What would destroy the ship is not pressure alone, but a sustained breach that allows water to enter and fill volume that currently holds air. The compartment walls are the real armor of a floating vessel. Pause here and think about the thing you are actually looking at when you watch a carrier at sea. You see the flight deck, the island, the antennas. What you do not see, sitting below the waterline, invisible and absolutely essential, is a three-dimensional grid of sealed rooms, each one doing its quiet work of holding air in place against the weight of the ship above it and the weight of the ocean around it. Those sealed rooms are the reason the ship floats. Not the steel. Not the reactors. Not the size. The air. The engineering principle behind the largest warship ever built is, at its core, the same principle behind a rubber duck. Enclose enough air in a watertight shape, and the ocean has no choice but to hold you up. The genius is not in discovering that principle. The genius is in scaling it to 104,000 tons, dividing it into 2,000 compartments, and making it survive. The bigger the machine, the simpler the trick that makes it work. Subscribe to see the hidden engineering behind the giants around you.